Hello, my name is Shigeki Ogose. I'm a Japanese. I'm a math teacher in Japan. So I'm very used to Mathematica, but this is the first time to use this for data analysis. The reason why I wrote this program is from the scientific interest, and the other reason is to have some stability of the mind by understanding the spread of the virus. Yeah, actually, by writing this program, I get the mind of stability a little bit, much better than before writing this one. Anyway, so I'm not a specialist of Mathematica nor COVID-19. So the result or the number of RT itself is not very reliable. Because to get the right number of RT, what is the most important? I think the most important part is distinguish the reliable data from unreliable data. So that's what I couldn't do. And to which extent you can rely. That also I couldn't do. So don't trust numbers. But I think the algorithm that I used in this program is interesting enough to upload this file. And I'm not an English native speaker. So if somebody is interested in writing subtitles with more natural English, it will be very much appreciated. Okay, let's start. Let me explain SIR model very quickly. S equals susceptible, those who can be infected. R is infected. R equals recovered, including the death, because if you are dead, you can no longer infect other people. C is confirmed, I plus R, and active cases infected. Then by SIR model consists of the three equations where beta and gamma should be constant. So first we start this one. The left hand dr dt. So which means that how many people recover per day. That is dr dt. Is proportional to infected. For example, if recovery date is 10 days, infected is 1000, gamma equal 1/10. It's the inverse of the recovery date. And d gamma dt equal 1000 by 1/10 equal 100 people per day, which means 100 people recover per day. So instead of thinking 1000 people recover simultaneously, almost simultaneously in 10 days, here we think that 100 people recover per day. That's what a scientist think. So gamma is the inverse of the recovery date. So it should be constant and not very different from country to country, okay? So next, move on to this equation. ds dt equals minus beta si. So the big difference is s here. See? So it says a number of susceptible, or you can use this one because these two equations are same. Number of new cases. Number of new cases is proportional to S and I. You can easily understand this is proportional to I, but why it is also proportional to S? So for example, if susceptible is 1 million and infected is 1000 people, in the early stage, number of secondary infected is proportional to this one, infected, and has almost nothing to do with susceptible. But in the advanced stage, when susceptible decreases dramatically, like 100,000, and infected 10,000. So this is a situation that there are not many food, for viruses. If there are many food, the speed only depends on the number of viruses. But if there are not many food, the speed also depends on how many foods remain. So that's what they say. So if susceptible is only 1/10 of 100,000, then absolute value of DSDT is 1/10 of the above. That's what they think. I think that so I can understand that if susceptible is 1/10, DSDT is less than the above. That I can understand. But they say that it's 1/10. I think that is too much. But anyway, that is their equation. And because beta represents the infectious speed and it can change by the policies of the people's behavior, such as lockdowns. So gamma is more, solid, more stable, more constant. But while beta depends on the, social behavior or the lockdowns and many things, so it can change. So that's a difference. Is it okay so far? So we get the basic equations. And we divide both sides of the old equation by gamma, and we define RT by S beta over gamma. And from this, R0 equal N beta over gamma. Because when T is 0, susceptible is equal to the whole population N. And RT equal R0 by S over N. Anyway, so when we divide all the equations by gamma, we get this equation. Okay. Okay. And if we substitute gamma t by t dash, we get this equation. And for example, if gamma equal 0.1, t dash equal 0.1 t. So if t dash equal 1, it's 10 days. So this equation means that you think by every 10 days. So ds dt dash means every 10 days, this number of people get infected newly. Okay? Every 10 days, this number of people infected. So per one infectious people, RT is infected throughout the whole recovery period. So that's why RT indicates the total number of people secondary infected by one person in his or her recovery period. And the same thing can be implied by RT equal DCDR. It's calculus, this one. This one and this one. From these two equations, by calculus, DC dr equal RT. So RT means that how many people are newly affected by one recovery, as one person recovered. So, okay, and from this equation, when I increases when RT is over 1 and decreases when RT is less than 1. So, as you know, viruses or the infected or recovered or so anyway, so they increase exponentially. So it is better to think on logarithmic graph because if something increases or decreases exponentially on logarithmic graph, it's linear, it's line. So it's better to think the logarithmic speed. So that's why we define mr equal d log r dt and mc equal d log c dt. Then by calculus, mr equal 1 over r by dr dt. And dr dt is here, gamma I. So we substitute gamma I. Then we get mr equal gamma I over r. So gamma equal r mr over I. Similarly, mc equals 1 over c dc dt. Then we get dc dt equals cmc. And RT equal, by definition, S beta over gamma. And we use this equation. So RT equal dc dt by I by gamma. So this one. So RT equal 1 over I gamma dc dt. And then we use this one. We substitute. We get this. And we substitute this. So there are many expressions for RT. 1, 2, 3, 4, 5. So we have to choose the proper equation for calculation of RT. Now I can explain my program. So this program calculates following these steps. First, calculate MCT by assuming C is correct. So by calculating MC, we get dc dt, and which means that we also get beta SI. So only we need to get the solution of this equation is gamma. And gamma can be calculated using MR. This is the formula. But I found that gamma is not reliable. So instead of using gamma obtained by data, I use gamma input. And if you give gamma, now you can solve the differential equation. So you can get SIR, the third step. By using SIR obtained by the solving the equation, you can calculate RT by this formula. So the reason for these steps is like this. I calculated the gamma of Japan, and as of March 13th, it was only 0.16, which means that so 6 days until recover. And I thought that it's too long. So I thought that R is very unreliable compared to C. Of course, C is not 100% reliable. And I think it is the professional's work. So how much, to which extent you can trust C or R. But I'm not a professional. So I can't do this. So my program is based on the assumption that C is correct, while R is not reliable compared to C. And my steps also had me notice that the fatality rate was too low compared to death and recovered. So if you check the statistics, death and recovered ratio is 1.6 or 1.7. So then fatality rate is 1/8 or something like that. It's too high. I thought it comes from the difference of the dates in hospitals for death and for the discharged. And by using this data, I calculated gamma at 0.33, but the recovery rate of Japan has shot up in the last week, so I recalculated gamma. This time I used OED and comprehensive judgment. I'll talk this later, to set the initial value of gamma at 0.5. So in the program, so now the initial value is gamma is 0.5, but you can change gamma in the program. And with my program, so if you increase gamma input, R will increase because gamma is the speed of recovery. So R will increase and R will decrease because I trust C, so R plus I doesn't change. So that's why, so I will decrease. So for more detailed information, please visit my website, but it's all written in Japanese. Data is downloaded from GitHub, Johns Hopkins University. Now I would like to show you my program. So this is epidemic curve, linear or log. And you can see the solution of ODE. On the right box, you can see RT or gamma T. RT is speed of infection, and gamma T is a kind of speed of recovery, very roughly speaking. And this data is as of March 28th. The confirmed cases is 16,000 and recovered is 15,000 and active cases 1,600. And this gamma input is the same as this one, and gamma T bar is the average of gamma calculated from data. So if you calculate gamma by data, it's 0.03. And I think it's very, very small because if you make inverse of this, it's 33 days to recover. It's very long, and there's another reason why I can't trust this data. This is a gamma curve from actual data. So recently it's 0.2. So recovery date is only 5 days. But 1 month ago, it was 0.02. So recovery date was 50 days, but now only 5 days. So you can't trust this data, can you? That is another reason. And there is one more reason. The third reason comes from solution of ODE. Now I set a gamma 0.03. So when you look at, when you compare these two curves, this is from ODE, this is the actual data. So if you compare these two recovered curve, if you take an average, they are very, well approximated. But when you look at the numbers recently, the actual number of recovery is 15,000, while the calculated number is much less than that. I think it's very strange. Rather than that, I think this number is better because these two graphs coincide recently, but there is a big gap here. But you can explain this by that because in chaotic situation and reporting recovered is not as important as new cases. So there's a gap here. But recently, as a chaos, it's not so chaotic now. So you can get the actual number here. So this may be the real curve of recovered. So there are three reasons why I would like to assume gamma equal 0.05. And the number of gamma should be the same from country to country. So I take this gamma for the default number. Okay. So let's see other countries too. First, we're going to start from United States. Gamma t is fine for United States. It's almost constant. This is RT. Gamma t average is only 0.01, which means that it takes 100 days to recover. I think it's very, very, very little. So I would like to assume that the real gamma is 0.05. So if I set the gamma to 0.01, but before doing that, 0.01, so those three curves coincide. But I said that I don't think it's a real curve. I would like to assume that the gamma is 0.05 for the United States. And actual recovered is 50,000 in the States, but I suppose that the real recovered number is about 122,000. That is my guess. And if my guess is right, RT in the state is now 1.0. So it's almost peak of infection, because when RT equal 1, infection becomes the highest, becomes the peak, takes the peak. So next, United Kingdom, it's almost same. Gamma t is very, very little. So next, Germany. In Germany, gamma t equals 0.068. Let's see gamma t. In the early stage, it's very strange, but I think it's because of there are not enough data. So when you look at from here to here, it's almost constant. And the value of 0.068 is very, reliable. So I think in Germany, all data recovered, infected are correct. And estimation of RT is maybe it's even lower than that, because all numbers are correct. So from my estimation, RT of Germany is now 0.5. So lastly, I would like to see the whole world. This is gamma. Average is 0.027. But I think it should be 0.05. And RT equal 1.2. That's my guess. If gamma is 0.027, RT equal 1.4. So I think it is between 1.2 to 1.4. Future of the epidemic. I'd like to calculate how many people will be infected in the world. And this epidemic curve for the future is based on assumption that RT is not changed by humans and lets nature go its course. This means that if susceptible becomes less, that means that food becomes less. So RT becomes less. RT changes in proportion to susceptible. So this is a curve. Now R0 equal 2. So this is susceptible. It's a ratio against the whole population. And the whole population is of the world is 7.7 billion. And this is susceptible. As susceptible decreases, RT decreases. If susceptible becomes half, 0.5, then RT is 1. So if RT is 1, DIDT equals 0. That is, it's a peak of infected. So this point is just below this intersection. And the value of infected, the ratio of infected is about 15%. You can see it by numbers. $1.2 billion. 1.2 billion infected. But this is the assumption from the assumption that R0 equal 2. But with our assumption, my assumption, it is my calculation, it's 1.2. So it is much less, about 1/10, 0.12 billion. And you can use this formula. This is the formula to calculate the peak of the infected. And now R0 equal 2, so it's 15.3%. But if R0 equal 0.2, it is almost 1/10, 1.5%. And the world population is 77.7 billion. So this is infected, okay, almost same height. And if the fatality rate is 2%, the death toll is sorry, I made a mistake here. This is the death toll, okay, about 2 million, 2.3 million. This is it. So, did you enjoy my show? I hope you enjoyed my show to some extent. I have 10 more articles about mathematics in my English site and 50 or more in my Japanese site, but with no subtitles. Sorry. You can download this file or you can download CDF file. You can download CDF player from Mathematica site and you can play and manipulate with CDF file free. I'll write down the link underneath the video. So I hope we can see again someday. Bye bye.